Again, and welcome to part 2 of lecture 5. This is a short little one in which we are going to take a little look at the interplay between ISM density and star formation intensity. Particularly, we are going to take a look at what is called the Schmidt-Kennicott law, or the Schmidt-Kennicott relation, which is an empirical relation that relates the surface density of the star formation rate to the surface mass density of molecular and atomic gas. What does this mean? Well, typically when we measure a physical density, it is the measure of that quantity per unit volume. But it is kind of difficult to see when we look at astrophysical objects where things are in the depth direction. So oftentimes we will simply integrate over the volume, and therefore we will make this a density of this physical quantity per unit projected area rather than per unit volume. So what that means is that the star formation rate surface density is the number of stars, or rather the number of solar masses worth of stars that are formed per year per projected unit area, which, according to the Schmidt-Kennicott law, is related to the surface density, again, the mass of atomic and molecular gas per projected surface area, by this power law, where we have two empirical coefficients. We have the coefficient B, which is empirically found to be around 10 to the minus 4, and the coefficient alpha, or the slope, power law slope alpha, which is again empirically found to be around 1.4. This correlation holds relatively nicely over a very large range of gas surface densities and a very large observed range of stellar or star formation surface density as well. However, there are a few caveats. First off, there is the uncertainty in the ratio of CO to H2 molecule in whatever gas we're looking at. That I have shown over here as a line of different slope, because that is basically going to give a different value of alpha than the one we have found if it turns out that we are wrong about our estimate of this number xco. Another uncertainty, or another caveat to this Schmidt-Kennicott law, is that if we look at it here in the low surface and the low gas density region, take a closer look here, what we can see is that even though it follows quite nicely up here, even though this law behaves quite nicely up here, once we get down to low gas densities, it actually looks like there's a general tendency that they drop below the Schmidt-Kennicott relation. Finally, there is also a third caveat, which is the disk thickness. A surface gas density can translate to a range of different physical gas densities, and that leads, as we can see, to this scatter around the Kennicott-Schmidt relation. But these caveats aside, the Kennicott-Schmidt law is still quite well behaved and quite nice, and a very useful and quite robust means of predicting star formation rate from gas density or the other way around. That was it for now. Thank you for staying with me this long, even though it wasn't that long this time. I will, in any case, be looking forward to seeing you in the next one. Thanks for now.